How would we really know if aliens exist? Not with flying saucers or a clear hello, but with faint clues. These might be a strange gas in the sky of a distant world or an unexplained signal. The challenge is simple but profound. We can't go there, so we have to decide what counts as proof from afar. And that question, what would even count as evidence, has shaped every attempt to search for life in the universe. In 1960, astronomer Frank Drake conducted the first real experiment. He aimed to listen for messages from another civilization. He called it Project Ozma. At the National Radio Astronomy Observatory in West Virginia, Drake focused a large radio dish on two nearby stars, Tau Ceti and Epsilon Eridani. They are both 12 light-years away. The idea was simple. If aliens were sending out radio signals, maybe the telescope would catch them. Radio waves were the perfect choice because they can travel very far through space without breaking apart. Humans had just discovered how powerful they were, so perhaps other civilizations had too. For weeks, Drake and his team listened carefully, sweeping across the radio spectrum. All they heard was a static. Still, the silence was not failure. Project Ozma helped scientists pick strong targets, set clear signal rules, and share their methods with others. From this modest start, the field of SETI, the search for extraterrestrial intelligence, was born. In 1977, 17 years later, astronomer Jerry Eman made an extraordinary discovery. He was using Ohio State University's Big Ear radio telescope. A strong signal lasted for 72 seconds. It came from the direction of the constellation Sagittarius. Excited, Eamon circled the printout and scribbled one word in the margin: "Wow." Ever since, it has been known as the WOW signal. The signal stood out. It came from a clear, steady frequency close to 1,420 megahertz, known as the hydrogen line. Since hydrogen is the most common element in the universe, many scientists thought aliens might use that frequency to send a message. But the signal never returned. After many follow-up searches, no one could explain it fully. It became SETI's most famous mystery, though not proof of alien life. These early efforts showed scientists a key lesson. Imagination should be paired with careful testing. Today, new projects like Breakthrough Listen, that launched in 2015, has scanned millions of stars with far more advanced tools. But astronomers now know that they may never hear alien radios at all. The first true clues may not come from signals. Instead, they might come from the atmosphere of distant planets. This includes gases, chemistry, and possibly signs of pollution or light. When scientists use powerful telescopes to study faraway planets, they're not looking for little green men waving at us. Instead, they look for two main kinds of clues: biosignatures and technosignatures. Biosignatures are hints that life might be living on a planet. On Earth, for example, plants make oxygen during photosynthesis. Without life, oxygen doesn't last long in the air. It quickly combines with other elements. So if we find a planet with oxygen, something must be putting it there. Another clue is methane. Here, microbes and animals release methane. If a planet has both oxygen and methane, it's exciting because the two don't usually stay balanced without life keeping them steady. Scientists also watch for smaller gases like dimethyl sulfide, DMS, which on Earth mostly comes from ocean life. To find these gases, the James Webb Space Telescope studies starlight that passes through a planet's atmosphere. Different gases block different colors of light, leaving behind patterns or fingerprints in the spectrum. These fingerprints tell scientists which gases are there. Technosignatures, on the other hand, are signs of advanced technology. They could be radio signals, laser beams, or even chemicals made by industry, like CFCs, chlorofluorocarbons. Some scientists even imagine spotting city lights on the dark side of a planet. But JWST can't find technosignatures. City lights would be way too faint compared to a star's glow. CFCs would also be too weak unless they existed in amounts thousands of times higher than Earth's. So JWST is like a doctor checking a patient's breath. It can tell if the air of a planet has oxygen, carbon dioxide, methane, or water vapor, but it can't tell if that planet has machines, cities, or technology. Future telescopes may be able to search directly for technosignatures. For now, JWST focuses on finding unusual chemical mixes, patterns that are hard to explain without life. And sometimes those patterns can spark headlines and debates, just like what happened with our own neighboring world, Venus. This kind of chemical mystery isn't just theoretical. Back in 2020, Venus made headlines with the claim, "Scientists find possible life on Venus." Venus is usually called Earth's evil twin. It's a hot, dangerous place. Its air is mostly carbon dioxide. Its surface pressure is over 90 times stronger than Earth's, and the heat is so intense it can melt metal. For a long time, no one thought Venus was a good place to search for life. But scientists weren't talking about the surface. They were looking at the upper atmosphere, where temperatures and pressures are calmer. There, they thought tiny microbes might possibly survive. The mystery was a gas called phosphine. On Earth, phosphine is made by certain microbes and by human industry. It doesn't usually appear naturally in big amounts. Years earlier, astrobiologists suggested that if we ever found phosphine on another planet, it could be a strong clue for life. So when two radio telescopes, one in Hawaii and one in Chile, spotted signals that looked like phosphine in Venus's clouds, the news exploded. Scientists reported about 20 parts per billion, which sounded small but was unusual enough to get attention. Suddenly, TV shows and newspapers were filled with pictures of floating alien microbes. But science takes time. Other researchers began checking the data. Venus's atmosphere is very tricky, full of sulfuric acid and other gases. Some of those gases, like sulfur dioxide, can look like phosphine in the data. And because telescope data has to be heavily processed, even small mistakes can create false signals. By 2021, most studies said the evidence wasn't strong. Some found no sign of phosphine at all, while others suggested it might exist at much lower levels than first reported. The claim of life on Venus didn't hold up, though the possibility of tiny amounts of phosphine has not been completely ruled out. For the public, this felt like a disappointment, but for scientists, it was a normal part of the process. Big claims have to be tested, retested, and confirmed. If results don't repeat, they don't count as proof. The Venus story wasn't a waste. It reminded scientists and the public that biosignatures don't prove life. Careful testing and repeated results are key. It also reignited interest in exploring Venus directly, with new missions now on the way. As the Venus debate quieted down, another mystery emerged. This one wasn't about a planet's atmosphere. Instead, it came from a radio signal sent by the closest star system to ours. In 2019, scientists from the Breakthrough Listen project used a big radio telescope in Australia. They listened for signals from space. A year later, while analyzing their recordings, they noticed something strange. The signal appeared to come from the direction of Proxima Centauri, the nearest star to the Sun. Proxima even hosts a planet in the habitable zone, called Proxima b, making the discovery feel especially tantalizing. The team named the signal BLC1. At first, BLC1 looked like the real thing. It was clean, narrow, and didn't sound like normal space noise. Even better, it only showed up when the telescope was pointed at Proxima Centauri. When the telescope looked away, the signal disappeared. For a while, it looked like the strongest candidate since the famous WOW signal in 1977. But science always asked for more proof. Other scientists tested the data in many different ways. They compared it with other telescope sessions and checked how the equipment handled signals. After months of work, the truth came out. The signal wasn't from aliens at all. It was caused by human-made interference, likely from electronics near the telescope. What looked like a beacon from space turned out to be noise from our own technology. For the public, it was a big letdown. First came headlines about a possible alien message. Then came the slow correction. Not aliens after all. But for scientists, this was an important win. BLC-1 lasted as a candidate signal for so long because it passed many early tests. That showed how much better the filters and methods are today. The lesson? Even the most convincing signals can vanish under close study. But that's a good thing. It proves scientists are careful and don't rush to claim aliens without rock-solid evidence. Each false alarm makes the next real discovery more trustworthy. The James Webb Space Telescope is offering new insights. While radio searches go on, it shows that clues often come from the chemistry of distant worlds, not just signals. False alarms remind us how cautious the search for life must be. but they also push scientists to look for new kinds of evidence. Astronomers now use the James Webb Space Telescope. It offers a new way to search beyond just listening for radio signals. When JWST studies a planet, it doesn't capture pictures of landscapes or cities. Instead, it analyzes the starlight filtering through the planet's atmosphere. That light holds hidden fingerprints of gases. JWST's instruments can separate them with great precision. Scientists use fingerprints to figure out the planet's air composition. Sometimes this chemistry reveals unusual hints. One of the first worlds it looked at was TRAPPIST-1b, a rocky planet about 39 light-years away. People were excited because the TRAPPIST system has several Earth-sized planets. But JWST showed that TRAPPIST-1b is far too hot, over 400 degrees Fahrenheit, and has little or no atmosphere. Without an atmosphere, there can be no water, no protection, and no chance for life. Next came WASP-39b, a giant planet similar to Saturn but much closer to its star. This time the results were thrilling. JWST saw clear signs of carbon dioxide, water vapor, sodium, potassium, and even sulfur dioxide. The sulfur dioxide proved that sunlight was changing the planet's chemistry. For the first time, scientists could watch chemical reactions happening in the atmosphere of a planet so far away. Then JWST studied K2-18b, about 120 light-years from us. This planet may be a Hyson planet with a hydrogen-rich atmosphere and possibly oceans below. JWST found methane and carbon dioxide, which fit that picture. There was even a hint of another gas called dimethyl sulfide, or DMS. On Earth, DMS mostly comes from ocean life. If that signal is real, it would be a major clue. But scientists haven't confirmed it yet. For now, only methane and carbon dioxide are certain. These discoveries show how JWST is changing our understanding of alien worlds. It can reveal which planets are too hot, which ones have thick clouds of strange chemicals, and which might have the right conditions for habitability. But JWST also has limits. It cannot see city lights, radio signals, or small amounts of pollution. Even if a whole planet were glowing with alien cities, the light would be billions of times fainter than its star, too dim for JWST to notice. That is why JWST's greatest strength is in finding biosignatures, the chemical clues that suggest life could exist. For signs of advanced technology called technosignatures, we will need future telescopes. Still, JWST is already building a library of alien atmospheres. Each new world it studies teaches scientists more about the possibilities and the limits of life beyond Earth. And among all those worlds, one in particular continues to capture our imagination more than any other. Proxima b, discovered in 2016, it orbits Proxima Centauri, the star closest to the Sun. At just over 4 light-years away, Proxima b is practically in our cosmic backyard. Even better, it sits in the star's habitable zone, the region where liquid water might exist. On paper, it looks like one of the best places to search for life, but the reality is more complicated. Proxima b orbits its star at a very close distance, completing one orbit in just 11 days. Because of this, it is almost certainly tidally locked, which means one side always faces the star, while the other side is stuck in eternal darkness. That would create a world of extremes, scorching heat on the star side and deep freeze on the other. Only a thick atmosphere with strong winds could spread heat around to make the planet more stable. The star itself adds another problem. Proxima Centauri is a red dwarf, and red dwarfs are notoriously violent. They send out powerful flares of radiation, far stronger than what Earth experiences. These flares can strip away a planet's atmosphere and make the surface unsafe for life. For Proxima b, the biggest question is not whether it's in the habitable zone, but whether it has an atmosphere at all. Without one, liquid water would be impossible, and life as we know it would not survive. This tension is exactly why Proxima b is so fascinating. It could be the nearest place where life might exist, or it could be a bare rock, blasted by radiation. We are close enough to study it with today's telescopes, but we still don't know the answer to the simplest question: does it even have air? The James Webb Space Telescope is helping, but with limits. JWST cannot take pictures of Proxima b's surface, nor can it detect city lights or radio signals. Its strength is in studying the starlight as it passes through a planet's atmosphere. If Proxima b does have air, JWST might detect signs of gases such as oxygen, methane, or carbon dioxide. These gases are most interesting when found together. On Earth, oxygen and methane balance each other only because of life. If JWST were to find that same balance, it would be a powerful hint that something unusual was happening. But JWST cannot find technosignatures. It cannot tell us if Proxima b has civilizations, machines, or lights. Despite what headlines sometimes suggest, scientists are not looking for Earth 2.0 with cities waiting for us. They are asking a simpler but vital question. Does Proxima b have an atmosphere that could protect and sustain life? Even a yes to that question would be a major breakthrough. It would mean that a rocky world so close to a fiery red dwarf could keep its air despite the star's violent flares. That alone would change how we think about habitability in the universe. This is why Proxima b holds our attention. It is both promising and uncertain, close enough to study but harsh enough to doubt. It reminds us that being in the habitable zone is not the same thing as being truly habitable. And Proxima b is just one example. The search for life often brings excitement, then caution. A strange signal or chemical might seem promising, but often fades under closer study. In the search for life, scientists often stumble across mysteries that at first look extraordinary. A strange flicker of light, an odd chemical in the air, or a radio signal out of place. Any of these can spark excitement. Headlines race ahead with talk of aliens. But over time, most of these signals turn out to have ordinary explanations. These moments are not failures. They are lessons that make the search stronger. One of the most famous examples is Tabby's star, also known as KIC 8462852. In the mid-2000s, astronomers noticed its light dimming in bizarre ways. Usually, when a planet passes in front of its star, the star's light dips in a regular, predictable pattern. But Tabby's star dipped at odd times and by huge amounts, sometimes as much as 20%. Nothing about it made sense. Some people even suggested it might be surrounded by giant structures built by aliens, like pieces of a Dyson sphere, a hypothetical megastructure designed to collect energy. The idea made for exciting headlines, but careful study told a different story. As scientists kept watching, they saw that the dimming wasn't the same in every color of light. Blue light faded more than red light. That was the clue. Dust, not megastructures, was the culprit. Fine grains of dust block blue light more effectively than red. What once seemed like alien technology turned out to be something much simpler: drifting clouds of cosmic dust. The same kind of pattern has repeated in other cases. Methane has been spotted in the atmospheres of some exoplanets. Because methane can come from life, the discovery often sparks stories about aliens. But methane can also come from volcanoes or other natural processes. Without more evidence, it can't be taken as proof of biology. We saw the same rise and fall with the claim of phosphine on Venus and the candidate radio signal called BLC-1 from Proxima Centauri. Both began with bold headlines suggesting possible life. Both ended with more careful studies showing weak or natural explanations. For the public, these reversals can feel disappointing. Each time, the promise of aliens seems to be taken back. But for scientists, false alarms are signs that the system is working. Every mystery forces researchers to sharpen their tools. Each correction improves filters, calibration, and methods so that future signals are tested more carefully. Tabby's star led to better models of dust. Methane debates pushed scientists to design clearer ways of telling life from geology. The Venus case reminded us that calibration errors can trick us, while BLC-1 showed how human electronics can mimic alien broadcasts. None of these events proved aliens exist, but each one made the search more reliable. That's the value of false alarms. They are rehearsals for the day when a signal or chemical pattern really does hold up under every test. And when that day comes, we will need telescopes ready to take the next step, to look closer, measure better, and confirm what is real. The search for life is far from over. In fact, it is only just beginning. The James Webb Space Telescope has opened the door, but it cannot answer every question. That job will belong to the next generation of telescopes, new eyes on the cosmos that are already being designed. Each one will push further than JWST, filling in the gaps and building on what we have learned so far. The first step will come in the late 2020s with the Nancy Grace Roman Space Telescope. Roman will carry a special instrument called a coronagraph, which can block out the blinding light of a star so that nearby planets can be seen directly. It's like holding up your hand to block the sun so you can spot the faint stars around it. Roman's coronagraph will mainly serve as a technology testbed, but if it performs well, it could capture some of the very first direct images of planets around other stars. It will also survey wide stretches of the sky, finding many new exoplanets for JWST and other telescopes to study in detail. Further into the future, scientists are planning the Habitable Worlds Observatory, HWO, a mission expected in the 2040s. While JWST was built as a general-purpose telescope, HWO will be designed specifically to search for Earth-like planets. Its mirrors and instruments will be tuned to detect and study atmospheres in incredible detail. Scientists hope it can find several biosignatures at once: oxygen, methane, and others. Then they will test if these fit together to suggest life. HWO might also detect technosignatures. This includes artificial gases from industries or strange light patterns. These signs could suggest alien technology. At the same time, giant telescopes on Earth will join the search. Projects like the Extremely Large Telescope and the Giant Magellan Telescope in Chile and the 30-meter telescope in Hawaii will surpass today's observatories. With mirrors as wide as 39 meters, they will collect more light than ever. This allows them to study the atmospheres of distant planets with great precision. Together, these space-based and ground-based telescopes will divide the work. Roman will find and map new planets. The giant ground telescopes will measure their atmospheres with sharp detail, and HWO will go after the ultimate goal, testing whether an Earth-like world around a sun-like star truly shows signs of life. The search will not be solved by one telescope alone. Signals must be checked again and again across many instruments and methods. But step by step, each mission will make the search stronger and more precise. With every new tool, uncertainty will shrink, and speculation will slowly give way to evidence. These new eyes on the cosmos will ready us for the moment we discover life beyond Earth. Life may be out there waiting to be found. Do you think we'll discover it? Comment down below.